In the last lecture, we talked about some methods of first order ordinary differential equations, and we also talked about one of the applications of first order differential equation, and it is about Newton's first law of cooling. Okay, we now have another application of first order differential equations. This application is about natural growth and decay. Here we say the differential equation dx by dt equals kx. Dx by dt equals kx. This is the equation of the application of first order differential equation for natural growth and decay. This differential equation is, here there's a question. It says, do you know what type of differential equation is this? That is separable differential equation. Okay, this is separable differential equation. This is separable differential equation. Okay, here we have k. K is a constant. That's a constant. And also x is the size of population or number of dollars. Also amount of radioactive. Here, the problems can be seen in these applications: population growth, compound interest, radioactive decay, drug elimination, and chemical reactions. We have the application of this first order differential equation in these topics. We have an example here. It says a certain city had a population of 25,000 in 1960. That means in 1960, the population of the city was 25,000, and population of 30,000 in 1970. In 1970, the population of that city becomes 30,000. Assume that its population will continue to grow exponentially at a constant rate. What population can this city planners expect in the year 2000? Look, here we have given the population of the city in 1960. And also we have given the population of the city in 1970. We should find the population of the city in 2000. We should find it. Okay. What's the starting time? Our problem is starting from 1960. Okay. That means at 1960, we need time to be 0. Okay. We say x is the number of population. We say x of 0 is what? Is 1960. Okay, because we let our problem is starting from 1960, so we let 1960 to be starting time, and start time is 0. So x of 0 is what? What's the population at 0? 0 means 1960. It is 25,000. Look here, we should write down the initial value. Okay, we should write down the initial value. That's why we start from 0. If we also can say at 1960, we can say that also, but it will be more complicated, and at the end we must get the same results. Okay. Okay, which one is earlier, 1970 or 1960? 60. So that's starting time. We go from 1960 to 2000s. Okay, that means 1960 is the starting time, and we let the starting time to be 0. That means x of 0 is 25,000. How about 1970? What's the time in 1970? If we count number of each year to be 1, that means x of 10. If 1960 is x of 0, so 1970 is x of 10. Is it? 1970 is 10, because From 1960 to 1970, it's only 10 numbers, 10 years. So x of 10 is what? 30,000. So how about x of 2000? What's time in 2000s? It's 40, is it? It's 40. What's x of 40? We should find x of 40. By using this equation, this is the equation which we use in population growth. We use this differential equation. And the given things in the example are only these two conditions. And what's required? We should find the population of the sea after 40 years. After 40 years. Okay. At starting time, the population 25,000. After 10 years, it became 30,000. So how about the population of the sea after 40 years? We should find it. First, in the first step, we should extract the information. Yeah, we say x of 0 equals 25,000. I'm going to write down them all here. And x of 10 is 30,000. So how about x of 40? First what? We should find this. Which equation do we use? We use this differential equation. dx by dt equals kx. dx by dt equals kx. So our differential equation is dx by dt equals kx. Okay, we use this differential equation in solving this problem. And the information, the given information are only these two conditions. And we should find the population of that city after 40 years. Let's use this differential equation, or let's first solve this differential equation. And then we apply the conditions to find the values of constants. Here, k is constant. And in solving the problem, we get another constant, which is c. Okay? After taking integration, we get a constant. That means at the end, we have two constants. By using these two conditions, we can solve, or we can find the values of constants for the equation. Let's solve it. We have dx by dt equals kx. As I said, this is a separable differential equation. So you should put dx with x in one side of the equality, and also dt with t in the other side of the equality. And here we can say this dx over x equals k dt. Is it? We just multiply by dt and dividing by x. We get this. Now, what should we do? Now we separated the variables. What we do, we are going to take integration for both sides. We take integration for both sides. For the left-hand side, it becomes ln x. The integration of dx over x is ln x. We get ln x equals kt plus c. kt plus c. Let's say c1. Okay. Now, how to get x? How to get x? Here we have ln x. How to remove that ln? We must take exponential for both sides. We take exponential for both sides. Take e for both sides. What we get? We get e to the power ln x equals e to the power kt plus c1. In the left hand side, these two are cancelled out. So what's remain here? Only x. What's left in the left hand side? Only x. We have x in the left hand side, and in the right hand side we have exponential of the sum two terms. So you can separate them. We get e to the power kt times e to the power c1. Is it? The multiplication of these two, we add their exponents. And we let e to the power c1 to be c. This is a constant. E to the power c1 is a constant. And we name it by another constant. Let's say it's c. And the equation becomes x is e to the power c, not c1, because we just replace this by c. And we get c e to the power kt. This is the solution for the differential equation. And now we must find the values of constants. We must find the values of constants. How to find the values of constants? We can find the values of constants by using the conditions. We have two conditions. X of 0 is 25,000 and x of 10 is 30,000. We apply these two conditions to get the values of C and K. So apply the conditions. Apply the conditions. The first condition is x of 0 equals 25,000. In the equation, in the last equation is x equals c e to the power kt. In that equation, we replace t by 0 and we replace x by 25,000. Okay, let's see what we get. So we get 25,000 equals c e to the power 0. Because if we replace t by 0, we get k times 0, 0. E to the power 0 is 1. E is a number which is raised to an exponent which is 0. So any number except 0, to the power 0 is 1. So e to the power 0 is 1. C times 1 is still c. That means c equals 25,000. This is the value of one of the constants. Now we return this to the equation. We return this to the last equation, and we get x equals 25,000 e to the power kt. We still have a constant in the equation. We must find it also. Then by using the second condition, the second condition is x of 10 equals 30,000. Okay, so what we do to the last equation, now this one is the last equation. For now, this one is the last equation. We apply this condition always to the last one. We apply the conditions always to the last equation. Now this is the last equation. In this equation, what we say? We say if t to be 10, x is 30,000. That means we replace x by 10 and we replace t by 10 and x by 30,000 in the last equation. Let's see what we get. We get 30,000 equals 25,000 e to the power. What's the value of t? T is 10. We replace t by 10 and x by 30,000. We get 10k. Okay. Now we divide both sides to find the value of k. We first divide both sides by 25,000 and we get 5. Here we get dividing both sides by 25,000. Okay, we did this step before. Okay, now what we get if we divide both sides by 25,000, we get 30,000 dividing by 25,000 equals e to the power 10k. Here we must find the value. we get 30 over 25. And we can cancel out them both by dividing both by 5. We get 6 over 5. In the left-hand side, we get 6 over 5. And in the right-hand side, you have e to the power 10k. Now, how to get the value of k? K is the exponent of e. How to cancel out this e? We must take ln. We must take ln for both sides. If we take ln for both sides, we get ln of 6 over 5 equals ln e to the power 10k. These two are constants. And we get 10k in the right-hand side. So the equation becomes, let me write down below. Okay. We get ln 6 over 5 equals 10k. How about k? We divide both sides by 10 and we get ln 6 over 5 by 10 equals k. So k is ln 6 over 5 dividing by 10. Let's find the value of it. We say 6 dividing by 5 equals 1.2. And we take its ln. Where's ln? This ln. Ln of it is 0.1823 and then dividing by 10. I'm going to calculate all in one step. So it's 0.018. That's approximately 0.018. That means k is 0.018. This is the value of k. If you replace in the last equation, what we get? So what's the last equation? The last equation is this one. Okay, we replace k by its value. What we get? We get x equals 25,000 e to the power 0.018 t. This is the equation. At any time, that means this is the number of population of the C at any time. So if t is 4t, if you want to find x of 4t, we just replace t by 4t and you get the result. Okay? We say which one? Yeah, yes, that's constant. Yeah. نخي كي ده دوستها هلو لا كيش ناقو كيو سيا كيش ناقو لا كي صفر نبو تي صفر بوي هو صفر. Okay, look, k and c are both constants. When you find it to the example, it's different from an example to another one. Okay, here to find x of 4t, it equals to what? We just replace t by 4t. That means to find the population of the C in 2000s, which is after 40 years from starting time. So x of 4t is 25,000 times e to the power 0.018 times 40. We just use them to find the population after 40 years. Let's find it. Okay, let's first find 0.018 times 40. We have 0.018 times 40 equals 0.72. If we take exponential for this, we get e to the power 1.2 equals 3 points. It equals 3.320 and so on. Okay, let me find again. We say it's 1.2 40 times 40 times 0.018 equals 0.72, sorry, 0.72. If we take E for it, we get 2. No, that's not 0.72. We say E to the power 0.72 equals to 2.05. Okay, E to the power 0.72 is 2.05. That means here it equals 25,000 times 2.05. Let's multiply these two and let's see what we get. You say it is 25,000 times 2.05. It equals 51,250 people. So the population of the city in 2000, it becomes 51,250. Sorry. How? Just what I'm telling you. Why is that? It is 51,250. So the population of the city in 2000 is 51,250. Okay. So this is the result of the population of the city after 40 years. Yes. No, I got open half thousand. Open half thousand. Exponential, but 20 open half thousand. No. Take it. Now there are some exercises for yourselves. Now we have another application of first order differential equation. This application is about electrical circuit RL. Okay. Here it's a resistance inductance. The problem is about resistance and inductance. We have these two in the differential equation. These are constants and they should be given in the example. Here we say we use this differential equation to solve the problems about electric circuits RL. I mean resistance inductance. What's this differential equation? This is a constant. If we divide both sides by L, what we get? We get di over dt plus R over L I equals E of t over L. Here, what's the dependent variable and what's the independent variable? The dependent variable is I and the independent variable is t. It's similar to dy by dx plus p of x y equals q of x. Look, in the right hand side, we have only a function for the independent variable. But in the left hand side, we have first derivative and also p of t, this is p of t, times the dependent variable. So this is linear differential equation. This is a linear differential equation. Okay, we just solve this linear differential equation for solving problems about electric circuits. Here we have given this differential equation. We say if the right hand side is a constant. We have two cases for the right hand side. It's either a constant or not. If it's a constant, it's a linear differential equation. We just follow the steps of solving a linear differential equation. We are going to find mu, and then we say the integrating factor of mu times I equals the integration of the integrating factor times q of t dt. After finding this integration, we get the result. And if the right-hand side is not zero, it's not a constant, sorry. If the right-hand side is not a constant, if we have sine or cosine in the right-hand side, we do the same. We follow the same steps. But in the right-hand side, I mean, q of x here is not a constant term. Q of x is a function of t. Yeah, as you see, only q of x is going to be changed. All are the same. We just follow the steps in solving linear differential equation. In the solution of linear differential equations, what we did, we said first we should write down the equation on the general form. The general form is that the coefficient of dy by dx must be 1, and then plus p of x y equal q of x. Okay, in the right hand side we have a function of x, and in the left hand side we have the first derivative, and its coefficient must be 1, and plus p of x times y. What we do after this, we are going to find the we are going to determine p of x and q of x. After finding p of x and q of x, after determining p of x and q of x, what we do, we are going to find the integrating factor, m of x is equal to what? Equals to e to the power integration of p of x dx. Okay, we are going to find this integrating factor. After finding this, what we do, we say y times mu of x, I mean the integrating factor, equals integration of the integrating factor times q of x plus c. That's all. We are going to find this integration, and then this dx. We are going to find this integration, and then we divide both sides by mu of x, we get the solution. But here, y is replaced by I, and x is replaced by t. That's all change that we do here. Okay? We just replace y by I and x by t. And then we follow this. We have only 3 steps in solving linear differential equations. First, writing down the equation on the general form of linear equation, and then finding the integrating factor, and in step 3 find this one. Here from this we are going to find y by dividing both sides by mu of x, but here we will have mu of t because our independent variable is t here. Here we have an example. Oh, there is no space here. Let me make a space here. We now have this example about electric circuits. We said for solving all the electric circuit problems, we use this differential equation. L times di by dt, I is the current, I is current. E is the voltage source, L is the inductance, and R is the resistance. Okay? To solve any problem related to electric circuit, RL means resistance, inductance problems. We use this differential equation, L times di by dt plus R times I equals E of t. Okay. And here we have an example. In the example, it says 2 9-volt batteries. This is the voltage source. This is the voltage source. That means 9 is E of t. E of t is 9. This is the voltage source. Okay. Any number with the unit of volts is E of t. That's the voltage source. It says two 9-volt batteries are connected to a series in which the inductance is 0.25. That means this is L. L is 0.25. It's 0.25 Henry. The unit of inductance is Henry. And resistance is 8 ohms. This is R. This is R. It says, determine the current. That means what's I of t? If the initial current is 0, as the initial current is 0, means I of 0 means I of t equals 0. I of 0 equals 0. It says the initial current, I is the current. We should find I of t, that means the current at any time. Here, it's given the initial condition. The initial condition is that I of 0 equals 0. It says determine I when t approaches to infinity. It's called steady state. If time goes to infinity and get steady state. Okay, let's write down the given information. We say E of t, I'm going to write down here. Example 1. This is example 1, solution of example 1. We have two 9-volt batteries. That means the right-hand side of the equation, I mean E of t equals 9. This is E. And then it says the inductance, which is L, is 0.25. L equals 0.25. And R, which is the resistance, it is 8 ohms. R equals 8. And it's given that the initial current is 0. That means I of 0 is 0. These are the given information. What should we find? We should find I of t equals 12. We should find I of t. And also, what's I of infinity? I mean, what's I when t approaches to infinity? What's I of t when t approaches to infinity? So here, we should find two things. First, I of t. After finding I of t, we approach t to infinity, and we get I of t when t approaches to infinity. What's I of t equals to what when t approaches to infinity? The equation was used for electric circuits for the first order differential equation is, we use this differential equation, L times di by dt plus R times I equals E of t. We use this differential equation. Let's replace L, R, and E by their values. L is 0.25. That means the equation becomes 0.25 di by dt plus R is 8. We replaced by 8 by its value. 8I equals E of t. E of t is 9. This is the differential equation. And we said this differential equation is the linear differential equation. This is, sorry, I is dependent and t is independent variable. Look, we say the general form of linear differential equation is in this form. Let me write down the general form of linear differential equation. We say dy by dx if our independent variable is x and dependent y. No, not but look, plus p of x times y, p of x times y plus q of x. وأجل هاتوا هاكو شيء ما ولسه أمشي ويبو كمبيوتر linear differential equation. بلا أقول له راس زر y بتواني إيه نشكل عبو يعني كالصفر يجنا بيت أو بيوتر برنامج. Why? Here we have no y in the right hand side. This is linear differential equation. Linear differential equation. Okay, and this equation is similar to that one. Our equation is similar to that one, but there in the general form you have dy over dx, but here we have di over dt. Only the variables are changed. It's okay. So this is a linear differential equation. What should we do first? We must make the coefficient of dy by x by 1. We should make it 1. How? By dividing both sides. We divide both sides by 0.25. Here, the coefficient of di by dt, the coefficient of the derivative, it must be 1. How to cancel out this 0.5 here? We must divide both sides by 0.25. So what we get? We get di over dt plus 8 over 0.25 I equals 9 over 0.25. Okay, 0.25 means 1 over 4. It means 1 over 4. That means 8 over 1 over 4, it is 32, is it? And then 9 over 1.4 is 36. It's 4 times 9. It becomes 9 times 4 or 4 over 1. 9 times 4 is 36. Dividing by 1 is still 36. So 0.25 means 1 over 4. So the results, we simplified first and then we try to solve. We get di by dt plus 32I equals 36. This is our linear differential equation. What we do now, we are going to determine p of x and q of x. What's p of x and what's q of x? Here, p of x is the coefficient of I, which is 32. And q of x is the right-hand side, which is 36. Here, p of x, p of t, sorry, not p of x, p of t is 32. And q of t is 36. We have these two. What we do after this, we should find the integrating factor. Means mu of t. What's mu of t? Mu of t is what's the integrating factor? E to the power integration of p of t dt. Here our independent variable is t, that's why we take the integration with respect to t. So it equals e to the power integration of what's p of t? It's 32. P of t is 32. We say 32 dt. What's the result here? What's the integration of 32? As 32t. We get e to the power 32t. This is the integrating factor. And then after finding the integrating factor, we say the dependent variable, which is I, times mu of t equals the integration of mu of t times q of t dt. We are going to replace q of t and mu of t by their values. We say mu of t is e to the power 32t and q of t is 9. Okay, so I times e to the power 32t equals the integration of mu of t is e to the power 32t times Q of t. What's Q of t? Q of t is 36. It is 36 dt. What's this integration? Here we are going to move this 36 out of the integration, and we get integration 32. So 36 of integration 32t dt. Here we must have the derivative of the exponent. That means the result of the integration is 1 over 32 e to the power 32t equals 36 times 1 over 32 e to the power 32t plus t plus c. Here we add c also plus c. So we get I times e to the power 32t equals 36, and 32 can be cancelled out by dividing both sides by 4. What we get? We get 9 over 4, 9 over 8. We get 9 over 8 e to the power 32t, okay, plus c. So now, how to find I? We must find I. How to get I? By dividing both sides by e to the power 32t. Dividing both sides by e to the power 32t. And what we get? We get I of t in the left-hand side equals 9 over 8. If we divide this by e to the power 32t, these two are cancelled out. Okay? So we get only plus c over e to the power 32t. This is the solution, or this is the current at any time. So what's the current if t approaches to infinity? If t approaches to infinity, we say I of t when t approaches to infinity. What we do? We are going to take limits for the right-hand side when t approaches to infinity. So we get the limit t approaches to infinity for 9 over 8 plus c over e to the power 32t. What if t approaches to infinity? T tends to infinity. We get c over infinity because e is 2.71. That means e to the power infinity is still infinity. That means c over infinity. A constant. It's a constant. If you multiply any constant to infinity, it's still infinity. If we multiply, look, if we divide any number by infinity, we get 0. We get 0. And here we have e to the power infinity. So the result is, sorry. Okay, yeah, it's a constant. It should be a number. Okay, that's constant. If it's be any number, if we divide by infinity, it's 0. So here, except 0, because 0 dividing by infinity is undefined. Here we say 9 over 8 plus c over e to the power infinity. What's e to the power infinity? It's still infinity. The denominator is still infinity. It equals 9 over 8 plus c over infinity. C over infinity is 0. So I of t when t approaches to infinity is 9 over 8. This is 0. Okay? So you say in the steady state, the current is 9 over 8. This is the solution for this example. Yes. Sorry,